Welcome to the Yaka Digital Network. If we look up at the burning surface of the sun and down at a single grain of soil, we are seeing the effects of the exact same energy source. The heat driving the stars and the nutrients sustaining modern crops both originate from a place we cannot see, the nucleus of an atom. Manipulating this invisible core produces intense forces known to physics, providing us a toolset that can power entire cities or save individual lives. To understand how this works, we have to look at isotopes. In nature, not every atom is born perfectly stable. An atom becomes agitated when it has an unbalanced ratio of protons and neutrons packed inside its center. Radioactivity is simply the atom's attempt to reach a stable state. To calm down, the agitated nucleus spits out pieces of itself or releases bursts of energy. So, if a nucleus is too heavy and needs to lose weight quickly, what exactly does it throw away? It uses alpha decay. The atom sheds weight by ejecting a heavy particle of 2 protons and 2 neutrons, a helium nucleus. Being large and heavy, alpha particles have very low penetration, stopped by a single sheet of paper. Beta decay occurs when a nucleus has too many neutrons. It converts one into a proton, firing out a high-energy electron. Smaller and faster, beta particles pass through paper, requiring a sheet of aluminum to block them. Even after shedding particles, the nucleus often holds too much energy. It releases this excess as a high-frequency gamma ray. Being pure energy, gamma rays move through paper and aluminum, requiring a heavy lead block to be absorbed. We can harness this instability to generate power on a massive scale. In modern power plants, we use nuclear fission, firing a neutron at a heavy uranium-235 nucleus to make it split. That split releases energy and more neutrons, hitting neighboring uranium atoms to create a self-sustaining chain reaction. To prevent an explosion, engineers drop boron or cadmium control rods into the reactor to absorb extra neutrons. This photographic source shows a facility using controlled fission to produce carbon-free electricity for thousands of homes. This is the opposite of nuclear fusion, the process seen here that powers the sun. Fusion forces 2 light hydrogen nuclei together under extreme heat and pressure to form helium. While fission is our current technology, mastering fusion on Earth would provide a continuous supply of clean energy, with harmless helium as the only byproduct. These same nuclear processes are providing localized solutions across Africa, starting with medicine. In medical radiotherapy, doctors use gamma rays from isotopes like cobalt-60 to target cancer cells. The radiation breaks the DNA of the cells, preventing them from multiplying. In agriculture, radiation is used to sterilize male tsetse flies. This stops the spread of sleeping sickness and protects the health of livestock. Researchers also use controlled radiation to induce mutations in seeds. This allows them to select for traits like drought resistance, vital for food security. Because radioactive decay is so predictable, archaeologists even use carbon-14 to date ancient organic artifacts, making nuclear science a tool that extends from food security to historical research. However, this technology leaves behind radioactive waste. We measure the danger using half-life, the time it takes for half of a radioactive sample to decay into a stable state. Because some isotopes have half-lives of thousands of years, nuclear waste represents a hazard that will outlast the civilizations that created it. Managing this requires sealing waste in lead-shielded containers deep underground to prevent it from ever contaminating the surrounding environment or groundwater. Nuclear processes offer a path to carbon-free power and advanced medicine, but we must manage this high-density energy with rigorous safety standards and long-term oversight. To explore more interactive lessons and digital learning materials, visit us at yaka.cc.